Hi there, I'm Stefan T. Lloyd, and welcome back to Core C++ Part 3. In this part, I'm going to be talking about overload resolution, the next step on our journey of what happens when you call a function in C++. Previously, we've seen name lookup and template argument deduction run when you write a function call. So if I say something like std sort of vbegin vend, okay, what happens is first name lookup runs to figure out which sort you want. Here I haven't said std double colon, so I'm assuming I've got either a using directive or using declaration that's dragging this in, or I'm relying on argument dependent lookup based on the fact that these things actually live in std. That's actually not a good idea because there's nothing stopping these from being raw pointers, which would not trigger ADL if it's like a vector int. Although in VC's implementation, they're always of class type. And then template argument deduction runs, as we saw in part 2, that figures out that, oh, I mean sort with random access iterators, that's cool. And finally, overload resolution runs, because what happens if there are multiple overloads of sort? In fact, there are. There's a sort taking two arguments, first and last, and then there's another one taking a comparator. It defaults to doing std less, the less than comparison. But you also get the opportunity to customize it and say, hey, I would like to sort this in reverse order by greater than. So the compiler needs to figure out which one you meant. In fact, in VC's own sources, the source file that runs overload resolution is called dymto.c for did you mean this one? Did you mean this one? And it just asks that question over and over. So the overload resolution is complicated enough that it deserves a full clause in the standard. A clause is one of these gigantic numbered sections. C++ 11 only has 30 of them, so a single clause is actually quite gigantic. Like all of templates fit into clause 14, all of overload resolution fits into clause 13, whereas name lookup, it doesn't even deserve a whole clause. It lives in just a section 3.4 in basic concepts. So overload resolution, it's actually quite complicated. When you're first learning C++, or even when you're just an intermediate programmer, you've got all these things, all these ideas being thrown at you. You've got classes and inheritance and whatever, and it all can seem overwhelming at first. It can often bite you if you're not paying attention to how you're constructing your overload sets. Once you know what sort of constructs to avoid and what sort of constructs to prefer, it's definitely not like a constant headache. But it can cause problems if you don't know the basic principles by which it operates. I've seen a lot of confusion, especially when people start using lots of implicit conversions. They're like, why is this not compiling? Why is it ambiguous? Or why is this totally weird overload being called? And if they knew more about overload resolution, they would be able to avoid getting into such trouble in the first place. So we're going to look at some crazy scenarios today, and some relatively simple ones. Whereas something like template argument deduction, it's complicated in its own ways, but I always like to say it plays this simple matching game. And there are some cases where it does something surprising, but I would say overload resolution has nastier surprises in store. Usually I can just look at a template declaration and a particular call, and I can just tell you almost immediately what template argument deduction will do. Whereas with overload resolution, I actually need to pick through the various criteria listed in clause 13 if it's anywhere near complicated. So in the case of this std sort call, that's actually very easy because here are the overloads that are available after name lookup and template argument deduction run. You would have two arguments. Actually, in this case, template argument deduction would snip out the third overload because we haven't provided that third argument and there's no default. But in the case where I just had, say I had a function foo, and I said something like, okay, I'm going to declare int foo taking a couple ints. I'm not even going to bother giving them names. And then I've got another one overloaded. Say I'm going to do in an int. Isn't it nice that we've got a type that's only 3 letters? And then I just call foo with something like 1122. What happens is that overload resolution sees, hey, there are two competitors. I like to think of them as going into an arena, fighting to the death. And one emerges victorious, in this case the one taking 2 arguments. And that's good. That's what the programmer expects. But the compiler had to follow a deterministic set of rules to give us this answer. So if you look at the standard E's here, I'm looking at the latest working paper, which is slightly after C++ 11. It really hasn't changed much so far. Overload resolution has this idea of candidate functions that are thrown into the overload set. We've seen how those are found. And then it's got this idea of viable functions. This is actually the easiest part. Basically, a function is viable if it's got enough arguments, if it's got enough parameters for the arguments being fed into it. So obviously, default arguments come into play here. In this case, there are no default arguments. So if you've got a 2-arg function and a 3-arg function, and you only pass 2 arguments, then obviously you want the one taking 2. The one taking 3 arguments doesn't even enter into the second part of overload resolution. However, what happens if you've got 2 overloads that have the right number of arguments, say something like this, where I've got int meow taking int. I'll just give you 1 argument, and then I say something like int meow taking const string ref. Okay, and then I call something like meow of 11, or meow, say I've got some string s somewhere, or I could say meow of peppermint. These are actually 3 different scenarios. The types here, I guess this doesn't really look like an S. This is an S. I'll say st. Here the type is int. Here the type would be an actual string. Let's say I've got a modifiable L value. And here the type is actually an array of const char. So this would actually be const char, and I'm not going to count how many characters in there, including the null terminator. String literals are actually arrays, even though they decay almost immediately to raw pointers. So what happens in overload resolution is says, okay, I see a couple of viable overloads. They have the right number of arguments, so they pass that test. Oh, and by the way, something that many programmers expect when they're new is that somehow return types matter in overload resolution, especially if instead of just calling a function here and then throwing the value away, what if I was feeding this, the result of the function to something else? Doesn't that return type matter? And the answer is actually no. The return type is just completely ignored during overload resolution. It works forward. So the arguments that you give to a function will select or declare an ambiguity which function is actually chosen. But what you do with the return type, that's determined after a particular overload wins overload resolution. It can never cause a particular overload to be preferred instead of another. So here the return type is irrelevant. I could have just said void. So the clause 13 has this idea of a best viable function, and this is complicated. It's probably not the worst part of the standard, but it has a lot of rules because programmers were very demanding. We throw a bunch of crazy overloads at the compiler. In this case, it's really simple. They could get much more complicated, coming from different namespaces, involving a whole bunch of different implicit conversions. And these rules, which are just written on paper, in this case PDF, have to produce a result that is intuitive to the programmer or declare an ambiguity when it really can't figure out what is desirable. So that means the rules are actually quite complicated. They have the effect of producing a reasonable result in most cases. Like in this case, nobody is surprised that meow of peppermint will call the one taking const string ref, even though the types there aren't identical. The array of const char n is convertible to a constant string ref, and yet it's not convertible to just plain int. So that's what this best viable function stuff is doing. It's got this whole define an implicit conversion sequence, whatever. And it has this idea that some conversions are better than others. And in this case, yes. In this case, I'm going a little too quickly. Here, if I call meow of peppermint, this meow of int, it passes the argument count test. It doesn't actually pass the viability test because there's no way to get from const char n to int. So that's actually, it fails the viability test, and we don't even get to the best viable function. Let me construct a case which is a little more complicated. So imagine here, let me include string. Okay. And if I've got void meow taking a const string ref s, and I say, actually I don't even care what the thing is, because I am just going to print that I selected this overload. Come on. And I have another one. Actually, let's template this to be fun. Template on int n. I could say size t here, but it will be fine. This is a non-type template parameter, which is not super common. And I would say I'm going to take a const char reference to an array of n of these. I could give this a name. In this case, it would go here. I suppose I haven't done a part about how C and C++ declarations work. They're parsed from the inside out. This almost never matters except when you've got crazy multi-level pointers, or in this case, references to arrays. In this case, you would put the variable name here saying R is a reference to an array of n const chars. In this case, I don't even care what the variable is, so I'm just going to drop that. I guess I could print it out, but I only care which one's being chosen here. And I would like to say whether this one is being chosen. Okay. And I can actually get rid of some of this white space because my window is very narrow. And then if I have calls like meow of per, and then if I have a string st of cat, if I call meow of cat, let's see what happens. So I compile, and because my string is named st and not cat, I should pay attention to my squiggles there. And now it succeeds, and we get printed that if I give it a string literal, I get the templated overload taking an array of n const chars, and if I give it a string, then I get meow of const string ref printed. So this is, again, intuitive, but here overload resolution had to do a little more work, because not only are the argument counts all correct, they all take one parameter, and not only do they pass the viability test in this case, but one is considered better than another. So here we've got per, which is an array of 5 const chars that I was able to count, the number of characters plus the null terminator. And template argument deduction runs, we find that this meow deduces n to be 5. And then this one, taking const string ref, is also viable because it's convertible. So then the best viable function rules come into play. Let's take a look at those. And it's got a rather hideous table. Standard conversion sequences, here it is. So it's got this notion that there's a whole bunch of conversions that the standard is willing to do. These are things like converting int star to constant star, various base to derived conversions, integral to floating point and back. Standard just loves conversions because as programmers, we just want stuff to compile. We don't want to explicitly write out every type transformation. And it has a ranking. Certain conversions are considered better than others. The overriding goal in all of overload resolution is if it's got to convert some parameters, it wants to do so with the least violence possible. The best of all is an exact match. When something doesn't require any conversion, it's like, yes, the programmer gave us type X, and they've got an overload taking type X here. I'm just going to invoke this. I don't need to worry about converting it to anything else. But if it has to do conversions, then it's going to select the least desperate one. So this ranks them in terms of exact matches, promotions, and conversions. And this all refers to earlier parts of the standard section or clause 4, which lays out all of the conversions that are possible. It's standard conversions. Again, the conversions are so complicated they deserve a whole clause to themselves. This is where the usual arithmetic conversions are defined, and that's a phrase that should strike terror into the hearts of C and C++ programmers because they can be quite tricky. So the overload resolution language also has the notion of user-defined conversion sequences. These are things like implicitly converting constructors, so one-arg constructors that are not marked explicit, or conversion operators. This is where you say operator T, and then T being a specific type or even a template, where you can go from a source type to some arbitrary type. So you could say, hey, I'm convertible to int, even though that's probably not a good idea. And then there's the whole idea of ellipsis conversion sequences, which is useful to template metaprogrammers, not so useful to most other people. And the implicit conversion sequence ranking considers user-defined conversions to be even more desperate than purely standard conversions. So if we go back to my example here, when I have meow here and I am trying to call one of these two functions, it says, okay, I could call the one taking const string ref. I would need to convert your array of 5 const chars to a stood string, and then bind a reference to it and slap constants on it. That's considered a user-defined conversion. Remember, according to the core language, the standard library is just another user. It's a very special user, that wrote code that comes with the compiler, but the compiler itself doesn't really care. So this is considered a user-defined conversion sequence, whereas this meow here, which takes a reference to an array of 5 const chars after template deduction runs, this is an exact match because this is exactly the type of the string literal per. There are actually no conversions required. All that we do is we bind a reference to it. So this exact match is far superior to a user-defined conversion. There's some language here below that says if you've got to use a user-defined conversion, that's actually strictly worse than something that's purely standard. And essentially nothing can beat an exact match. So that's why we get the intuitive result that the one taking an array of const char wins. Whereas if I call meow with something that's a stood string, in this case, this overload is an exact match. I can just bind const string ref to a stood string. That's good. And this one is not viable because stood string is not convertible to an array of const chars or const char star. So this doesn't pass the viability, this one doesn't pass the viability test, and this one wins by default the 2 sweetest words in the English language. So that's a relatively simple example. Now I'd like to show you one of the comments on part 1. Somebody asked me, Ivan, what happens when you've got an overload set, hopefully this is visible, where you've got templates taking a const t ref and a const t star and you give it something like an int pointer. This has somewhat unintuitive results, so let's see what happens here. Let me get rid of this. And what if I say, let's have templates here. Template, type name t, void foo, taking a const t ref. Again, I don't really care what's being passed when I'm exploring overload resolution. I just want to see which function is selected. Because overload resolution only cares about types and never cares about values. And I'll print this. Or I could have template, type name t, void foo, const t pointer. I actually had to think about this when the example was presented to me. It all made sense though. So cout string, and I'd like to print that this is a const t star. Okay. And then what if I print here? I've got an int star. Value doesn't matter, so initialize to null putter. And then call foo with p. So the programmer who wrote this is not an overload set that I would write, would probably expect the foo taking const t star to be selected. Because this says, hey, I just take pointers and I don't actually care about modifying what they point to. So I can just say const there so I can accept pointers to const. And then I'm going to go do something pointerish to them. And then it's got this competing overload that says, I'll take arbitrary stuff. I'm not interested in modifying it. But I'd like to, not take pointers. I'd like this one to absorb any pointers that are being given to me. So if I'm calling foo with p, the intent of the programmer would probably be for this foo taking const t star to be selected, and yet that's not the case. So let's see what happens here. Of course, if I'm showing this to you, you'd expect something non-intuitive to happen. So let's compile and see what's printed. And the program prints out foo const t ref. So even though I've provided this overload taking const t star, I'm getting the const reference. So what's happening? Is this a compiler bug? It's actually not. This is what the standard mandates. But the way to get here is somewhat tricky. Remember, I warned you, overload resolution can be tricky. So what happens here? Well, let me scribble on the whiteboard. So in this case, I'm just going to omit the template type name t. I've got a foo taking a const t ref, and then a foo taking a const t star. Okay, and my argument type is int star. So template argument deduction runs, and it tries to figure out what could t possibly be here? So this one is actually easy. We need to do this first because after template argument deduction runs, these signatures are added to the overload set as if we had written non-templated functions to begin with. A tiebreaker would come in later if a template tried to compete against a non-template function and they were both equally good matches. In that case, the tiebreaker steps in and says, you know, these are equally good, and usually I would say they're indistinguishable and ambiguous, but you've got a non-template here that can only accept this one type. I'm going to select that one. In this case, there are no non-templates. Everybody's a template, so that tiebreaker rule is not relevant. So here, it's not too surprising. Template argument deduction says, okay, this is going to stamp out an overload, a specialization according to standard ease, taking constant star. So what happens here, and this is where the fun begins. Remember I said you need to know all the steps that are performed. Template argument deduction looks at this and says, okay, if I say const ref, that's the same, but I'm going to write it flipped so it's more obvious. This is a reference to a const t. So what is t here? Well, it's an int star. So I actually get a foo taking int star const ref like this. So the overload that's being stamped out is something that takes a reference to a const pointer to modifiable int. So this foo will not be capable of reseeding the pointer itself. I couldn't say in here, if this is, you know, const ref little t, I couldn't say like t equals null putter because I'm binding a reference to a const pointer. But I could write through it. I could say dereference my t and then go assign, you know, 5 to it or something. So the question is, after template argument deduction runs, given the argument of type int star and the overloads here reference to const pointer to int, I'm reading backwards technically inside out, and then a foo taking constant star, which one is better? And we've already seen the answer. The answer is that this one's better, but why is that? Well, they're both viable because we can see that it doesn't require anything ridiculous like converting a std string to an int. But one is being considered better than the other. Why is it? Now, this is one of the interesting things about writing code at compile time, and overload resolution happens at compile time, is it's quite difficult to get the compiler to tell you why it selected something. Usually this happens with templates, where template argument deduction does something and it's like, why are you choosing, you know, t to be this? With overload resolution, in some respects it's even worse because the compiler is just selecting a function to be the best viable function. In this case, because everything succeeds at compiling, it doesn't tell you why that thing won. It would be nice to have, you know, some compiler option that said, hey, could you like print verbose output about why you're selecting this thing? But in this case, the compiler is just completely silent. When something is ambiguous, then compilers will often help you, saying, hey, you know, I'm seeing these two functions and yet they're ambiguous. That gives you more of a foothold. But in this case, the compiler just says, wow, you must mean X, and the programmer didn't really mean X. So now we need to figure out why that's the case. So let's analyze the simpler potential call here, where I've got my int star, and what happens if I call foo taking constant star. So that's not an exact match. The types int star and constant star are different types. We would see this if we were writing explicitly or partially, or in this case explicitly specialized templates. They're just completely different types, as different as int and double. Yet they're convertible. I can convert from an int star to a constant star. I just can't convert the other way. So that's where all of this stuff about conversions comes in. Let's look at the standard conversion sequences. Fortunately, there's nothing user-defined here. And here's that table of doom that I had mentioned. So I will cut to the chase here. The converting of a int star to a constant star is considered a qualification conversion. That's mentioned in section 4.4. Of course, we could read all of clause 4 to figure this out. And this explains that, let me see if I can zoom in here. It says a PR value, which we can ignore, of type pointer to CV1T, this means const volatile qualifiers, or maybe nothing, can be converted to a pointer of type pointer to CV2T if CV2T is more CV qualified than CV1T. So what the standard is, the standard is actually simple, although if you're not used to reading it, it can seem scary. It's saying that you can go from a pointer to X to some pointer to something else if you're adding constness to it, which is very intuitive, and there's something about volatility there that we don't care about. In this case, that's what's happening. We can go from int star to constant star because we're applying constness. That's a totally safe conversion. So it's a qualification conversion, and this, surprisingly, I was actually surprised by this when I looked it up, is considered an exact match. Here the rank is what matters for determining the goodness of a conversion. It's got this special category qualification adjustment, but as far as overload resolution is concerned, it's actually considered an exact match. I would actually have expected it to be slightly worse than that. So here we've got an exact match. Well, what about binding int star to a reference to const int star? Is that an exact match? Is it worse? It certainly can't be better than an exact match. And so let's see what that does. There's actually a whole section here, 13.3314 in the latest working paper, reference binding. And it says when a parameter, in this case the parameter reference to const, pointer to int, of reference type binds directly. And here this is a phrase of power, and we can see because it's actually citing another section of the standard, to an argument expression, in this case p. The implicit conversion sequence is the identity conversion. Unless the argument has a type that it's a derived class of blah, and then we can just tune out because we don't have any derived classes here. So the question is this a direct binding? And if it is, then we've got an identity conversion here. So let's go look at this hyperlinked section here. So now let's go over to clause 8, declarators, and then 8.5 is initializers. This is actually another relatively scary section in the standard. This explains how things get initialized and whether that initialization is actually possible. Certain initializations are forbidden, like trying to initialize a pointer to int from a pointer to constant. That would strip away constness. So this initializers, it's got a whole bunch of subsections here. The one we care about is references. What happens when you initialize a reference from something else? This section 8.5 keeps coming up because it's not only used if you say something like int ref r equals, I can't really scribble here, int ref r equals n, but also this is an initialization. This also comes into play when I call a function because I'm initializing the parameters from particular arguments. So here we want to know what would happen if we initialized this int star const ref from int star. And this section it's long and horrible, and it's even better now that there's r value references. But skipping over some stuff, it says a reference to type CV1T1 is initialized by some expression of type CV2T2 as follows. And then if the reference is an L value reference, and then the initializer expression is an L value, that's actually what we've got here, and these things are reference compatible. This basically means that you're not trying to strip away constness. Then it says, then the reference is bound to initializer expression L value in the first case. Cool. This is in fact so common, it's essentially the first case that's mentioned. Then it's got a whole bunch of other stuff about what happens if you're binding to a class type and the class is a conversion to blah. And these scenarios actually do occur in real code. Here we've got a relatively simple one, even though it looks scary. And then it's got other stuff about what happens if you bind to something that requires a temporary to be produced, whatever. And then there's a little bit of language here at the end, which is the language we really care about. So we saw that the first case activated, where this L value reference binds to an L value, everything's good, they're reference compatible. It says, in all cases except the last, when we've got to make a temporary, the reference is said to bind directly to the initializer expression. This phrase of power is put in italics because it's used elsewhere. So even though we are binding this reference to const to this int star, it's said to bind directly because we're just applying constants to it. We know we're not making any temporary, we're promising within foo not to modify the thing without casting away const. But we're not performing any actual conversions on the object itself. The object here is a pointer. We actually don't care what it's pointing to. We're just binding a reference to const to it. So that's a direct binding. And then going back to the overload resolution stuff, it said that if we've got this reference binding, it's 13.314. When it binds directly, it's the identity conversion. So what do we see here? This one here, this is identity. Okay. And it's also considered an exact match. Okay. This one was considered an exact match too, but it's not an identity. It required that qualification conversion to apply constness to the thing that is being pointed to. So I had mentioned that only the rank mattered when considering whether a function is better or not. That was a white lie. In fact, there are more tiebreakers. The overload resolution rules have just tiebreakers upon tiebreakers that can be interesting. So the section that matters here is 13.332, ranking implicit conversion sequences. So we figured out, yes, the functions are viable. Here are the sequences that would be required to invoke these functions with the argument. So which one is better? This is actually where the heart of overload resolution is. And so here's that language I'd mentioned earlier, where a standard conversion sequence by itself is better than anything involving a user-defined conversion sequence, a UDC. And then it's got some bit about the ellipsis. Then it says, two implicit conversion sequences of the same form, and these are both standard conversion sequences, so this applies, they're considered indistinguishable unless one of the following rules applies. So it says, standard conversion sequence S1 is better than standard conversion sequence S2 if, and then it's got a whole bunch of bullet points. I can actually show you how many bullet points it's got. It's got a bunch. And so let's scroll back up here. One of the ones that usually activates is if the first one's rank is better than the second one's rank, then the first one wins. And that's referring to the ranks in the table here, exact match, promotion, conversion. But that here, in this case, they're both exact matches. We don't even get that far because the very first bullet, let me see if I can zoom in this a bit. It says S1 is better than S2 if S1 is a proper subsequence of S2. And this is actually a very intuitive rule. Overload resolution says, okay, if I would have to go this distance to get from argument type to parameter type, and I'd have to follow the exact same path, but go a little further to get from this argument type to this other parameter type, then I would prefer to use the one that goes less distance because it's a strict subsequence. So it says if S1 is a proper subsequence of S2, and then it says comparing the conversion sequences in some canonical form, then S1 is just better. And here it says the identity conversion sequence is considered to be a subsequence of any non-identity conversion sequence. If you're familiar with sort of math language, this should be relatively straightforward. It says if you didn't have to move anywhere, that's the identity conversion sequence, then that's always better than having to perform any work whatsoever. And that's the case we've got here. They've got the same rank, exact match, but one is an identity. That's the one binding the reference. The other one is not an identity. It involves this qualification conversion, and that slight little bit of having to apply constness to the pointed to thing is more distance than just binding a reference directly. That's why this one wins. So as far as overload resolution is concerned, it did the right thing. It sees a reference being bound, and that's just totally identity, no modifications required. Then it sees a pointer conversion. It's like, you know, that pointer conversion involves a bit more work. I think the programmer would be less surprised if I just bound this reference to the exact type of the thing and then applying constants on it. So that's why this const ref is selected. Yet if we were looking at it from a further distance, the original code that was written, it can seem unintuitive because I wrote const ref and const star, and it's like, you know, both of these say const, one is ref, one is pointer, the thing is a pointer. Why isn't this happening? That's why. It's because overload resolution, it doesn't know any better. It's just doing what the programmer said. The programmer didn't just say what they wanted precisely enough. Now there is a way to write a function that special cases pointers without running into this. I had mentioned at the beginning that I don't run into this sort of problem because I know to avoid it. I don't write templates like const ref that are very grabby. When you write a lot of C++, especially complicated, template stuff, you get a feel for what functions, especially what templates, how they behave with others. And I view templates as being very greedy, which is often a good thing. If I say foo taking const ref, this is willing to bind to essentially any t and apply constants to it. And because the nature of template argument deduction it'll deduce t to be exactly the argument type that's being passed in. So it's going to produce exact matches all over the place. Those exact matches will win over almost anything else. Like here, where we require just a little bit of a qualification conversion, or even a plain function. If I had a non-template function here that required anything beyond an identity conversion, the template would be selected. Remember I mentioned that tiebreaker, non-templates beat templates only when they would otherwise be exactly as good. But if the template is willing to adapt itself to be exactly what's needed, the template wins. Templates are greedy. Perfect forwarders are the most greedy of all, and we've actually run into a fair amount of trouble implementing the STL with perfect forwarders just grabbing all sorts of stuff that we kind of don't want. So at a high level, the way to avoid this sort of thing is be careful. When you write a greedy template, especially a greedy perfect forwarder, try not to put anything else in that overload set, except for things that are just totally non-viable, like things that don't even take the right number of arguments. That's okay. But if things do take the same number of arguments, and one of them is a template, especially a perfect forwarder, try to think really hard about avoiding this. So in this case, this overload set, we've seen it's no good. We could try tweaking it. We could try some enable if, which would actually be a really bad idea here. Or we could just completely restructure our code. So imagine I've still got the same calls down here, where I'm calling foo with a star, and I just want a special case. What happens if I have pointers? So I'm not using strings here. What if I include type traits? So here, type traits, this is standard library stuff, so we're just going to treat it as opaque magic. This is a bunch of helper classes that can tell you properties of a type. Is this thing a pointer? Is it a function? Is it const qualified? Is it void? And then there's also transformations, which we won't get into here. So the way I would like to approach this is write this foo taking const t star, and then have it call a helper. And I'll have two kinds of helpers. So I'll say template type name t, okay, void helper. I could make this inside a details namespace or something, but this is just an example code. And I'm going to also take const t star, but I'm going to take false type. This is a stood false type. It's just a tag struct. It's as if I had said inside namespace stood struct false type, and then it's got a static const bool in there. In this case, we don't actually care what it is, and we certainly don't care about its value at runtime. We just want the type as a tag. And here I can print that this thing is not a pointer. Like this. And then I could have the exact same code, and I will use a horrible technique of copy paste. I could say true type, and say I'm a pointer. Now if I wished, I could get a little more tricky here, because here I'm just taking a reference to t. What this is asserting essentially is that t is going to be a pointer. I could start saying, like, you know, t star here, but at this point I'm not going to do that. I want something that's very simple. So here, helper is overloaded. These are literally the same name. They have the same number of arguments. They just differ in their second argument, false type or true type. And then what foo can do is say, okay, I've got to have a name here, and I'm going to call my helper. I'm just going to pass down the t. In this case, I'm passing down a const tref. I don't need to worry about perfect forwarding or anything. And then I'm going to tell the helper what I would like to do. So I'm going to say, is this thing a pointer? T. So is pointer t, it comes from namespace stood in type traits. This is a type. I would like an object of this type, like this, and then, sorry, is pointer t is a struct, and I want to get the nested type. I've got IntelliSense working in my head. And I've got to say type name here. We saw what happens with double colons in part 2. And so this is a type. I would like an object of this type. So if I say, the way I would write it is I would just say pren here, and then call it a day, finish my function call. You may consider this, especially when you start off writing code like this, to be confusing. So I could have just a helper type def. I could say type def, here's the real type, and then the fake type could be x. Okay, so type def is pointer t nested type x, and then here I could just say make a temporary object of type x. This might be easier to parse if you're not used to writing this metaprogramming like this. And then I've got my foo p here. I can also throw in another one. What if I call foo of a number selected completely at random? So what I would expect here is to see I'm a pointer, and then I'm not a pointer. And let's see if this all compiles. I don't see squiggles here, so I think it's good. And it builds. And I see, yes, foo p, I'm a pointer. Foo 1729, not a pointer. So that crazy scenario which we had originally where the pointer one selected const ref, that's been completely avoided because I restructured my code differently. Here I'm calling foo, and foo is just a single function. So overload resolution says, hey, you just win by default if you're viable. Then inside, I ask at compile time, hey, is this type t, which I've deduced to be either int star or int here, is this a pointer? And then type traits does some magic, and this is actually something that anybody could write very easily with a partially specialized helper struct. This returns a type that is either true type or false type. And then I pass just a temporary object of either true type or false type to my helper. And I also pass the t that I'm actually interested in if this were real code. Then overload resolution comes, but now it's a very simple form. I've sort of confined the aggressive, crazy power of overload resolution that's willing to look at just completely bizarre argument types and parameter types and say, the programmer wanted X, Y, and Z, and this one is kind of viable and it's better than everybody else. So let's just call this, and I hope that the programmer wanted this. In this case, I have sort of channeled its power down to saying, okay, I'm just going to give you some t, have template argument deduction, figure out the exact same answer that it did for foo, that part's simple. And this other type, it's either true type or false type, and they're totally not convertible to each other. So whatever this type is, we're just going to deterministically select either this one or this one. We don't need to look at any of the bizarre rules of clause 13. We just know that if the thing is a pointer, then I get a true type here, otherwise I get false type. And then I can do whatever I want. Then because the presence of this extra argument, this temporary of a tag type, is selecting either the first one or the second one, at this point I could get trickier and I could say, okay, I know if t was a pointer, I know I'm going to call this one, so I can go mess with the type of this first argument without changing the result of overload resolution. Now if I screw it up, if I try to get a pointer to something that's just completely the wrong type, like what if I make this one take a double pointer and I only passed in a single pointer, then I would get a compile error, but at least I wouldn't get something where overload resolution just starts selecting something that I didn't want. So I sort of avoid this problem by being aware that templates are greedy, and because they produce exact matches all the time in overload resolution, I structure my code differently. And this is actually, it's not really any more work. You know, I've got 2 helpers here and then a wrapper, and if somebody's looking at IntelliSense for foo, they would see, oh, I've just got a foo taking const ref, and internally it does something special. And if I had 2 overloads, then they would see the 2 overloads. So it's a little different in terms of IntelliSense, but it still produces a relatively simple result. So that's a complicated example. Now I'd like to show you one thing that, in this example, using knowledge of how overload resolution works, I was able to get the desired result by structuring my code differently. It's not quite completely magical, and I can show you that with an example from the standard library, but treating it as opaque magic. I won't be digging into STL headers today. So imagine that I've got derived classes. I've got a struct base, like this. Then I've got a struct derived. They probably should contain stuff, but here I only care about the types, so I'm not going to put anything in them. Derived derives from base. I hate the terms subclass and superclass. I believe it was actually Strausstrup who invented the terms base and derived to avoid the ambiguity of, wait, sub is below super, which way does it go? I hate that stuff. So base and derived it is, and we've got struct more derived, derives from public derived. Okay. So with this here, I no longer need type traits, but I will need memory in a bit. Then if I've got functions void foo, and in this case I just want to take a base star, I could say completely random string, and then I've got another one taking a derived star, there we go, not feeling particularly inventive for this one, and then in my main, imagine that I've got a more derived pointer. This would point to some object, but again, I only care about the type, so I don't really care what it is. MD, I'll put her. And then what if I call foo with MD? So we had seen how overload resolution, it tries to determine the least amount of violence it has to do during a conversion. We know that more derived star is convertible to both derived star and base star. We know that such an initialization would compile. And yet, because of this hierarchy, this chained hierarchy, we know that going from more derived star to derived star is shorter, it's less distance than going from more derived star all the way up to base star. So we would hope that overload resolution would say, both of these are viable, but I think you want this more specific one. Returning specific functions as opposed to more general functions is the prime goal of overload resolution. So we would expect this derived one to be printed, and in fact that is what happens if I haven't had hilarious typos. Build succeeded, and we get the derived message. So even though this produced an intuitive result, there has to be language in the standard that told the compiler to do this, and it is hiding in the conversion stuff. Let's go find this. It is in the ranking implicit conversion sequences. So here we had just seen that S1 is a proper subsequence, then something about the ranks, and if we scroll down, yes, here we go. So it says standard conversion sequences are ordered by their ranks. Exact match is better than promotion, which is better than a total conversion. And it says two conversion sequences with the same rank are indistinguishable unless, and then it throws some tiebreakers at us. And it says, here we go. If class B is derived directly or indirectly from class A, and class C is derived directly or indirectly from class B, this is the more derived base hierarchy that I had. It says going from C star to B star is better than converting C star to A star. This is literally the case that we just wrote, and it even has a helpful example here that it says calls FB star. So there's a dedicated rule in the standard just for making this work because, and this is a bit about standard ease, if the standard did not contain that rule, then it would be considered ambiguous. It would have no way to tell between the two functions. If something made it unambiguous, then the standard would have no reason to go out of its way to have this dedicated rule. So a dedicated rule in the standard is always a signal that it's trying to do something specific. That's what's going on here. So let's try a case where I've got these same declarations here. Let me stop my program. Now imagine I've got some shared putters. Shared putters, they're smart pointers, and they attempt to imitate raw pointers as much as possible, except for their reference counting magic. So if I've got a shared putter, and again, I don't care about their values, and suppose that I've got a shared putter of derived, and I'm going to call that SPD, and I don't actually care what it is, and then my foo here takes, I'll take by const ref, shared putter to base. Shared putter should be passed if you don't really care, and if you really do want a shared putter, you should pass them by const reference instead of by value, because that avoids unnecessary ref count operations, which are not free, especially on architectures like ARM instead of x86. Okay, shared putter derived, that looks good. Okay, so here if I'm calling foo with SPD, again this is asking overload resolution to do some work for us, and we would expect that this foo taking const shared putter derived would be called because that's an exact match. We just bind a reference and apply constness to the object itself, but we're not performing any conversion. This other one would be viable. We can convert from shared putter derived to shared putter base because the standard library has specified such a conversion. But that's considered a user-defined conversion. Standard library is just another user, and an exact match is way, way better than a UDC. So we should see whatever derived printed here, and indeed that is the case. We compile, and everything's good, and we get whatever derived again. So what if I go back to that more derived case where I ask it, okay, consider going to derive, consider going up all the way up to base. Will shared putter exactly mirror what happened with the raw pointers? Because the standard library is specified very intelligently. It's trying really hard to imitate raw pointers, going so far as to provide these implicit conversions to imitate the pointer to base conversions that we're familiar with. So if I had a shared putter to more derived SPMD, and I call foo with SPMD, what will happen? Well, because I'm asking the question, it will fail to compile. And let's go look at the output window for a bit. We're already getting a squiggle. We can look at the squiggle. The squiggle says, error, more than one instance of overload function foo matches the argument list. And if we look at what the VC compiler itself prints, it says, of course the font is gigantic to make it visible, it says error C2668 foo, ambiguous called overloaded function. So here overload resolution was not able to select a single winner, and it declares an ambiguity. It says, hey programmer, I don't know which one you want. Please tell me, either by structuring your overload set differently or potentially converting your argument before you call me with something like a static pointer cast in this case. It says, you know, I could call foo taking a shared putter to tie where tie is derived, or I could call this other one you've got shared putter to tie where tie is base, where the argument list is a shared putter more derived. So we've seen that more derived star converting to derived star is better than more derived star going all the way up to base star. Why isn't shared putter doing the exact same thing? Why doesn't it have the same technology? And the answer is, the thing about the raw pointer was powered by a dedicated rule in the standard. It said here that raw pointers are special cased, even though they would be ambiguous in this hierarchy, that if it sees that converting a raw pointer to some intermediate base, it's better than going all the way up to a higher base. Shared putter, even though it's gone out of its way to be really, really similar to a raw pointer, in the end, it's not part of the core language. It's part of the standard library. It's just user code as far as the core language is concerned. So even though it's got these clever conversion functions, they're still just user-defined conversions. And there is a rule in the standard that, and I won't try to find it here, that aside from some certain cases, which don't apply here, all user-defined conversions are considered indistinguishable. If the standard sees that you're invoking a converting constructor or an implicit conversion operator, then it has no idea which one would be more intuitive than another. There's no way to annotate such constructors or conversion operators saying, hey, by the way, I should be considered like a pointer to derived conversion. As far as the compiler is concerned, these shared putter conversions are exactly the same as converting a const char star to a stood string. So when it sees two possible conversions going from shared putter more derived to shared putter derived, or shared putter more derived to shared putter base, even though as a programmer we can see which one we want, the compiler is not smart enough and has not been instructed to be smart enough by the standard library, because there's literally no way in the language to say that, hey, this UDC should be considered better. Shared putter has some interesting technology, and I know this is treading a little close to standard library territory, where using enable if and is convertible, it can disable its implicit conversions if they would simply never compile at all. So if my overload set here involves something like a shared putter int, that would not be considered viable because I can't go from a more derived star to an int star. So that would be totally snipped out of the overload set because the standard library has gone out of its way. In this case though, both of the overloads are viable. And there's no way, aside from this very blunt hammer of enable if turning on and off implicit conversions, to say, wait, they should both be on, but prefer this one. And I expect actually that the standard will never sort of be extended to make that reasonable, because this case is relatively obscure. My usual response to people when they ask, hey, could C++ do X, is, don't you think C++ is complicated enough already? This is obscure enough that I don't believe that it's worth some sort of special rule, new syntax, and new pages of standardese to allow someone to say, hey, you know, these UDCs, you know, this one is better. So if you encounter this sort of case, just be aware that you probably need to add, in this case, a static pointer cast saying, hey, this thing should really be considered a derived, or write your overload sets in a different form. So that's it for part 3. If you have questions for what you'd like to see in future parts, let me know in the comments. See you next time.